Hello, welcome to your physics teacher. In today's lesson, we're actually going to be looking at a very hard subject. We're going to be looking at vectors in 2 dimensions, and we're going to be looking at how to break them down into components. In other words, the rectangular coordinates. We're going to be looking at how to add vectors using components, and then we're going to try to see if we can add 2 or more vectors together. So today's lesson is very difficult. Please take it slowly and then make sure that you watch the parts that you're confused about again and again. So we're going to try to ultimately develop a strategy to take care of vectors in 2 dimensions. So make sure that you stay tuned for that strategy, which will make your life a lot easier for the rest of the course. So what you're going to learn now is going to be useful for the rest of the course and in grade 12 as well. So let's get started with question number 1. Question number 1 asks us, break each vector down into an x component and a y component. So the first one, here I'm just going to redraw it quickly. And the first vector that we're given, they give us the angle is 50 degrees. And the length, notice that there's no arrowhead, so there's no hat on top of the delta D. So the scalar portion is 20 kilometers. To find the x and y components, you have to imagine a projection, or in other words, just completing this triangle along the x and the y component parts. So those are the 2 lines that are drawn here. So here we have delta dx, and this is delta dy. Now notice how I've attached them. They're attached head to tail, because the sum of the x component plus the sum of the y component gives you back the original vector. This is the reason why we use rectangular components. So let me make that clear. So our original vector, which is delta d, is just the sum of its component vectors, delta dx plus delta dy. So this is going to be useful when we're trying to add more than one vector. But for now, all you need to know is that for each vector that we have, you can break it down along the x portion of it and along the y portion of it. And the direction does make a difference. So that's why you have to take this into consideration. So notice now that if we were to redraw this triangle, we have 20 kilometers, which is delta d. Delta dx is the x component, which we don't know. And delta dy we don't know as well. But we do know that this angle that was given to us is 50 degrees. Now out of construction, because the x and y coordinate system is perpendicular, we have a right angle triangle. So this makes it easy because now we can just use SOHCAHTOA, sine ratio, cosine ratio, and the tangent ratios. So a useful strategy at the beginning, as a beginner level, just write down cosine of the angle 50 degrees. And remember, cosine is ka, which is adjacent or hypotenuse. So that would be delta dx over delta d. Right, so if we're considering from the angle 50 degrees, the adjacent side is delta dx and the hypotenuse is the 20 delta d. We can multiply both sides by delta d, which will isolate delta dx, which was our unknown. So that's delta d cosine of 50 degrees. Delta dx equals to 20 cosine of 50 degrees. So let's calculate this. That's approximately 12.9 kilometers. And now to find the y component, we're going to use the sine ratio. Technically, you could use tan, but don't. As a beginner, always use cos and sine. So sine of 50 degrees. Remember, sine is so it's going to be opposite over hypotenuse. So from the angle 50, opposite is going to be delta dy over hypotenuse, which is delta d. Multiply both sides by delta d, so we get delta dy equals to delta d sine of 50. Delta d was 20, so 20 sine 50. Let's put this into a calculator. 20 sine 50. That's approximately 15.3 kilometers. All right, so that's what they wanted us, right? Break each vector down into an x component and a y component. So we finished. That was part A. They didn't specify to find the direction, but the direction is already what we've drawn. The x component points to the left, which is west, and the y component is pointing north. So if we want to add direction, we could. You know what? Just to be safe, let's do that, right? Because it was a vector quantity. All right, so that was A. That was pretty straightforward, so not so bad. So what are the steps? You should redraw your vector. You should find the x component and the y component by lining it up with the axis. Redraw your triangle, making sure that you remember that this is a right angle triangle, so you can use SOHCAHTOA. And then you're going to use the cosine ratio and the sine ratio to isolate for the components. So that's how we found the two x and the y components in this case. So let's see if we can do the other ones, but this time I'm going to go a little bit more quickly. Okay, so for part B, let's draw our vector. Our displacement vector in this case is 15 kilometers. The angle that they gave us is 80 degrees. And the components in this case, notice that it points south and a little bit to the west. So the x component points to the west, and the y component points south. And notice that they're connected head to tail, which is what we described before, right? Because the components add up to the whole. So in this case, we're correct. So now all we have to do is redraw a triangle, and then we're going to use SOHCAHTOA. Okay, so remember, when you're trying to find the components, you're going to use the sine ratio and the cosine ratio. So from the given angle of 80 degrees, you can label this as your opposite side, OPP, This is your adjacent side ADJ and the hypotenuse HYP. So that should help you out to remember the trig ratios instead. So now let's write down cosine of 80 degrees is going to be adjacent or hypotenuse, so delta dx over the hypotenuse delta d. So this means delta dx is delta d cosine of 80. Putting in the value, it's going to be 15 cosine of 80. So let's calculate this. Okay, we get for the x component, it is approximately 2.6 kilometers. And remember, it was pointing to the left, which is west, so we have to write as the vector delta dx 2.6 kilometers west. So once you use the cosine ratio, now you're going to use the sine ratio. So sine of 80 degrees. Remember, sine is going to be opposite, which is delta dy, or hypotenuse, which is delta d. So we can isolate for delta dy. Putting in our value, you get 15 sine of 80 degrees. And that's approximately 14.8 kilometers. And for the direction, remember that the y component was pointing downwards, so that means it's south. So you have to write the direction as well. 14.8 kilometers south. Now, maybe at this point, you start to realize a pattern here. Notice that the x component is always cosine of the angle, and the y component is sine. Likewise, look at this one. The x component was cosine of the angle, and the y component was sine of the angle. So this pattern is only true when the angle is always given closest to the x-axis. So I'm going to show you maybe in the third example why this is not always true when the angle is closest to the y-axis. So again, the pattern holds true only when the angle is closest to the x-axis. So let me write this down. Right, so this is a very good note for you to write down. So if the angle is closest to the x-axis, then the x component is cosine of that angle and the y component is sine of that angle. So make sure you make a note of this, and that way you have it on your own notes, okay? Now let's do one more case to show you that this is not true if the angle is closest to the y-axis. Okay, so now let's do question C. Let's draw a coordinate system. Let's draw the vector. And the angle is given closest from the y-axis, 65 degrees. And the length of this vector is 40 kilometers. To find the x and the y components, you have to go along the axis. So along the y-axis is pointing up, and we want to attach it head to tail. And along the x-axis is pointing to the right. So we can label it as delta dx. And the other one is delta dy. Now let's redraw this. and what we were given was the delta D is 40 kilometers. This angle inside was 65 degrees, and we're looking for the x component and the y component. So remember what I said before, if you use cosine, it's for the x component if the angle is closest to the x-axis. You can use sine if the angle is closest to the x-axis to find the y component. But now that the angle is closest to the y-axis, we can't use that idea anymore. So let me prove to you why not. So considering the angle 65 degrees, and because here we have another right angle triangle, from the 65 degrees, we can label the opposite side, the adjacent side, and the hypotenuse. So in this case, cosine of 65 is going to be delta dy over delta d. So you see right away, cosine is actually connected with the delta dy, which is the y component. So if we put in the value for delta d, that's 40 cosine of 65. So let's plug it into our calculator. 16.9 kilometers. You see, but the main point was if the angle is closest to the y-axis. Now in this case, cosine ratio is the one we use for the y component, which is the opposite of what we had before. Now let's use the sine ratio. So sine of 65, sine is opposite, which is delta dx, or hypotenuse, which is delta d. Isolating for delta dx, we get delta d sine of 65. So plugging this in, 40 sine 65. Which is 36.2 kilometers. So the key takeaway here then is going to be if the angle is given closest to the y-axis, then we can't use the previous strategy. But what if instead we remember that in any right angle triangle, in the rectangular coordinate system, which is 90 degrees, if you're given the angle closest to the y-axis, you can always just find the angle closest to the x-axis by subtracting it from 90. So I'm going to quickly show you that, and then that way we'll be convincing ourselves to always just use closest to the x-axis. It will make our life a lot easier. So remember before I had my delta d, and I had my y component going up and my x component going to the right. But the same thing can be written if instead I first start off with my x component and then I go with the y component. So I get back the same sum, because it doesn't matter whether you add delta dx plus delta dy or delta dy plus delta dx. So the order of addition doesn't matter. And this means that we have two triangles, but they're really identical in this case. So if this one here was 65 degrees, and that was closest to the y-axis, all we have to do is subtract it from 90 to get the related angle. So this is 25 degrees. This is delta dx, delta dy, delta d. Now what I'm trying to show you is that if we use the angle closest to the x-axis, we're going to get the same value for the x and the y component. So delta dx will be delta d cosine of 25, and delta dy will be delta d sine of 25. using the previous argument that we made before. So let's plug in the values. 40 cosine of 25, 36.2, and then 40 sine of 25, 16.9. So you see, we actually get the same x value and we got the same y value. So that's why whenever you're going to use vectors in 2 dimensions and then they give you the angle closest to the y-axis, the easiest thing to do is just find that related angle, which is closest to the x-axis, and keep in mind our formula that we said the x component is cosine of the angle and the y component is the sine of the angle. So this will make your life easier for every single question in grade 11 and 12 and beyond. So please take the time to practice it and you'll get really good at it.